Welcome to part 2. We had a technical failure. So, now up there this will work. Uh-oh. How's my internet? Okay.
Whoa.
All right, here you go. Oh, come on, go. I'm still loading. Chrome is really terrible. Also, the internet is really terrible.
Internet's pretty terrible, yeah.
I mean, in general. Across the board. Okay, there it goes. All right. Which one is which? Okay, so there's a red dot and a green dot. Oh, let me put this up here. No, I'm on the wrong camera. I'm just going to be on the wrong camera. Notice how the red dot is tied to a crest, and the green dot is tied to the gap between the packets. So which one is which? Which one would you call the phase speed?
Probably the red one.
Because that's going with the crest. It's the phase of the wave that matters. And the green one is the group speed. So if I've done this in the past, I don't have it off the top of my head right now to give you a great lecture on this, but I'll show you how it basically works. So so this is x and this is t. If I have sine kx minus omega t, that looks like this, right? If I keep t fixed, then it's just sine kx. If I keep x fixed, then it's just sine omega t. This goes up and down, right? That makes sense? You can think about this as k times x minus vt. And this is just a pattern. Like, this is just translation. X minus vt is just this thing slides over with a velocity v. Does that make sense? So if I take x naught, this is x minus vt, this line here. This part of the phase will stay right there. So if I pick this part of the wave, it will travel with x minus vt. It'll just go that way if this is time and position. Does that make sense? So x minus vt is a phase. V here is omega over k. I just factored that out of this. Okay, does that make sense? So the phase speed is the one that you get out of this, the inside of the sine and the cosine, because that's the phase of the sine. The phase of the sine is whatever the crap is inside. The group speed, if I have a packet like this, a packet like this has more than one frequency in it. If it had one frequency, then it would be the same the whole time. I need to have more than one frequency to have it have some shape. So I have a distribution of frequencies. And if I look at the distribution of frequencies in k space, if I have a Gaussian in my distribution of frequencies, Gaussian is just e to the minus k squared divided by some width. Oops, let's just make that a k squared. If my wave packet looks like a Gaussian, then my real space packet also looks like a Gaussian, because the Fourier transform of a Gaussian is a Gaussian. That's a useful thing. And then if I say, how does this move with time, then you got to do a stunt that I can't remember that I'm going to try to, I'll dig it up. and do that derivation. This winds up moving with the speed vg, this whole packet of stuff, that's d omega dk. And it's a derivative because this has to have a bunch of different wavelengths in it for it to make sense as a packet. Otherwise, it's only one wave forever. That's not a great derivation. This part is okay. So remember this. The phase speed is the stuff that's inside the sign, and that's just algebra. The group speed is one that takes me like 20 minutes to actually derive. But one of the cool things is I can also, when I do that, I'll do that on Thursday. Because you get Heisenberg's uncertainty principle out of that too. And that's pretty cool. Because I don't have any quantum mechanics here, and I still get something that sounds quantum mechanical. So I'll do that on Thursday. Any other questions on this board of stuff, which is really a bunch of stuff?
Yeah, I had a question.
Yeah.
I don't think I got the one linear equation that you get at the end of step 4.
Oh yeah, that's the wave equation. It's linear because it only ever has one row at a time. Okay, what's next? Method of characteristics. So now all of that work is really about throwing out this second term. This second term is a problem, and I'm going to show you using Berger's equation why this is a problem. Because Berger's equation is just like this one with the stuff taken off. So Navier-Stokes has this term, Euler has this term, Berger's has neither of these terms. Berger's is simpler. The only reason that I'm showing you Berger's equation is it's a simple version of Navier-Stokes. It's the only reason people use it in the first place, because we want to say, well, what does this part of the equation do? So it just says dv dt plus v dv dx equals 0. This is a much simpler equation because there's no right-hand side. dv dt, I'm going to write it up here, plus v dv dx equals 0. And we'll be in one dimension here, so this v is just vx. You don't need to worry about this being a vector right now. How do I solve this equation? There's an easy way to solve this equation, and I'm actually going to show you with a simpler equation. Let's get even dumber. Scalar advection. Scalar advection says dq dt plus a dq dx equals 0. Now, okay, this is a very similar equation to this other one that I wrote. The only difference, now I've got q. Doesn't really matter what q is. It's a thing that depends on space and time. It is a quantity of, let's say, pollutant or concentration of vinegar in your sauce or whatever. So this is some conserved quantity. A is just its speed. A doesn't change with space. So scalar advection, A is constant. Let's talk about this for a second. So what the method of characteristics says, so let's look at this equation. This equation is just chain rule of the full derivative. dq dt equals 0, and dx dt equals a. So this is one partial differential equation. I can rewrite it as two ordinary differential equations. This is a thing you can do a lot of the time. It's pretty handy. So what does this say? It says q is constant. Almost. Q is constant when dx dt is a. So these two things have to happen at the same time. So if I look at x and time, if I pick a position here, if I have a blob of stuff at this position, so say this is a river and it's going in one direction, the blob of stuff is just going to be advected by the scalar advection in this direction. It's going to go like that. So along this line, dq dt is 0, so q is constant. Does that make sense? So what I can say is q of x and t is equal to q of x naught, t naught. That's easy. This is the initial condition. So if my initial condition looks like this, let's solve this equation real fast. So this equation says that a equals x times t plus, x equals a times t plus x naught. That's this one here. That's easy. So I can just rewrite this, x naught equals x minus at is a line. Now, q of x minus at, 0. That works fine. So q of x and t, this is the concentration of stuff as a function of position and time, is just the initial condition shifted. So at a later time, if this is what my initial condition looks like, at a later time I've just shifted along this line. So that should look like this. That should be shifted over that way some. Does that make sense? Okay, now I'm going to do the same thing. Except now I'm going to do Berger's. Oh, no, that's still x. Now, if I do the same thing but with Berger's equation, Berger's turbulence is making turbulence with Berger's equation, which is the thing that people like to do. So if I do the same thing with Berger's equation, everything I said is the same. So dv dt is 0, along dx dt equals v. V is a function of space and time, but the full derivative is 0. Yeah?
Why do you use dv over dt is equal to 0, dx dt is equal to v when it's dv dx is equal to 0 in the original equation?
This is dv dt. This whole thing is capital V, capital T equals 0. And you chain rule that out, it turns into a v, and you get a d into dx. It's a good question. So v is constant along this, but now, so with scalar advection, all my lines are parallel. But now my lines don't have to be parallel. My line is going to depend on what the velocity is at that time. So now my lines can go away from each other or go towards each other. So I can have a situation where my velocity is this way, over here, and this way over here, and they are moving towards each other. That is problematic. That makes a shock. That makes an infinity. So, okay, x naught equals x minus at, v naught equals 0, so v equals, so let's do an example. I want to leave all this here, so I'm going to do this example little here. So let's say that v equals minus mx plus b, where m is a constant and b is a constant. So here my initial velocity v x is like this. So this bit here is moving faster than this bit here. So you know what happens by experiencing traffic. If the thing behind you is going faster than you are, you're in trouble unless that thing stops. And in traffic, that thing has a person in the inside. But if you have hydrodynamics, it's just going to shock. and we can talk about this. So let's say v equals minus mx plus b, x here, x is x naught is x minus at. A is v now. I just did the same thing, but I just swapped a and v. I just traded. So now I can say that v equals minus m times x minus vt plus b. Okay, I just plugged in what x is. Now I'm going to solve this, and I get that v equals, I'm going to skip a little bit of algebra, I'm also running low on time. Do a little bit of algebra to solve for v, and you get b minus mx divided by 1 minus v minus mt. So here we can see that at t equals 1 over m, what happens? If I plug t equals 1 over m in here,
infinite speed.
you get infinites. That's problematic. Infinities are problematic. We don't like them. This is infinity in a finite amount of time, too. Infinity at t equals infinity doesn't matter. Infinity at t equals something real that I can actually achieve. That's problematic. So what the whole purpose of going through this is to show you that this part here, this v that's in front of this grad v, if it's constant and boring, then my solution is constant and boring, and it just moves. I have my initial conditions, and my solution just translates if the velocity is boring. If the velocity is the velocity, then I have something that's going to shock, and it's going to blow up, and it's going to turn into infinity. So that's really the magic of this term here. It also gives you chaos. It gives you small-scale structure. It gives you all kinds of interesting stuff. I spent most of the day getting rid of it and showing what happens if we get rid of it. Then we want to talk about what happens if we keep it. So we see that it blows up. Now, this is Berger's equation. It blows up. I can show you, I just did show you Berger's equation blows up. There's an initial condition that I can hand to Berger's equation, and in a finite time I get infinities everywhere. It is not clear if I add the grad p term on if it still blows up. That's an open science question that if you answer it, you'll be famous. Like win $1 million famous, like no joke. But also, it's a super hard problem, and nobody else has sorted it either. So that's not career advice. Okay, I think that's all I'm going to say today. Does anybody have any other questions about anything? Oh, actually, what time do I go to? 2:35.
I don't remember.
At least, right?
Yeah, I think I still have a couple minutes. I don't go till 2:20. I still got a couple minutes. So I'm going to talk about other new stuff. Yeah, let's talk about the ranking Unionio. Because, oh no, I didn't want to erase that. I still need that. Okay, so we get a shock. Things are going to shock. What is a shock? A shock is a discontinuity. That's a boring word to write. Okay, a shock is a discontinuity in what? In all of the variables. So what we're going to do is we're going to say, okay, I just have a shock. It started somewhere. It's going somewhere. We'll assume that it's, yeah.
Is the line thing an actual shock, or is it just you breaking off what you were talking about?
This is a shock.
Okay.
So a shock is a step function in your quantities. So there's two sides, 1 and 2, and I've got density on one side and density on the other side, velocity on one side, velocity on the other side. So I have these two states. So how can I figure out the relationship between these two states? Let's start with continuity. d rho dt plus grad rho v equals 0. So we'll assume that we're in steady state. that means that my shock is just moving. That means that the partial with time is 0 because it's not evolving with time. So I'm just left with grad rho v equals 0. So I integrate this. It's a full derivative, so it's just the things at the endpoints. So I'm going to integrate this equation from point 1 to point 2, and I'm left with rho 1 v1 minus rho 2 v2 equals 0, or it's right up here, rho 1 v1 equals rho 2 v2. So if I have a shock like an explosion, something where the velocity, where the density perturbation is large compared to the density, then across that shock, the momentum is constant. Does that make sense? This is really the mass flux. The mass flux is constant, but it's also the momentum, so that's kind of handy. So that tells us one thing. We need some more information about this. So let's look at the momentum equation. So this, what I just did was I integrated stuff. The integral of grad stuff equals 0. So then stuff evaluated at 1 and 2 equals 0. So the jump in stuff is 0. This is one of the useful reasons of writing things as conservation laws, which I'm going to make you do for homework, is rewrite these guys as conservation laws. No, I'm only going to do momentum. I made you do internal energy last time. So if you do this for momentum, you get d by dt of rho v equals minus grad rho v plus p delta ij. That delta ij is important because this is a tensor. Let's give us the notation, the indices here, so that we can see what this equation is actually telling us. D momentum I, so the I component of momentum, is div of momentum I times Vj plus the pressure term. So you can, this is equivalent to these two equations. If you take these two equations, you pack them together and you get this one. Now, if I want to know what the momentum jump is across my shock, I set the left-hand side equal to 0 because we're going to say we're in steady state. And then I've just got an integral over this derivative. So that tells me that rho 1 v1 squared plus p1 equals rho 2 v2 squared plus p2. That make sense? Rho. And then if you take the third equation, the third equation is for internal energy, and so this one is d by dt of what? 1/2 rho v squared plus rho e. That's all my energies, kinetic energy and internal energy, equals minus div rho v 1/2 rho v squared plus rho v e plus v times p. You may not be able to write that one down like that, but once you're done here, you will be. So this is just rho times v times the internal energy times the kinetic energy, the internal energy, and this is the work making new internal energy. We rearrange this, and this is the enthalpy kind of turns into all of this. So that's why enthalpy and work are buddies. So I just integrate this, and I get this across the jump is constant. Or you can do a little bit of algebra, and I'm going to leave this bit to you because it's, I think, useful algebra to do. You get a simpler equation that I don't have here, and I think I'm not actually going to say anything about it at the moment. So there's a third equation that I didn't write down, and I could look it up in the book, but I don't care about it right now. So there's a third jump condition. What's the purpose of these jump conditions? The purpose is, if I know what one side is and I know there's a shock, then it doesn't matter what the internal structure of the shock is doing. So it could be like this. As long as there's some kind of discontinuity from one point to the other point, and it's in steady state. It could be doing this. It could be doing this. It could be doing all kinds of stuff. Okay, it's got to be monotonic in a function. But it doesn't matter. The structure of the shock doesn't matter because we've integrated across it. And we've gotten rid of all the other details that we don't need. Okay, so Rankine-Hugoniot. So this is the Rankine-Hugoniot jump conditions. And the last bit I have 5 minutes, and then this is going to cover everything that's on the homework, I'm pretty sure. So this kind of feels like I have a really nice technique for dealing with an equation where I get rid of the linear things and then kind of a grab bag of random things to try if you have the nonlinear terms, because the nonlinear terms, we don't have general tools for dealing with nonlinear equations. So Rankine-Hugoniot jump conditions are one. This other one is another technique. So what we're going to say is, how do we get a shock wave? Well, we have an explosion. Why do you randomly make bad noises? Okay. I have some kind of explosion, like a firecracker, or a nuclear warhead, or a conventional warhead, or some kind of explosion, or a supernova. Supernovas going off look a lot like nuclear weapons. The only thing, so this is going to make an explosion, and it's going to be a spherical shell that expands outwards. And in years where I've planned ahead, I have good videos of this because there are some really cool videos that you can find of supersonic things with explosions. The only thing that so we've got this explosive front, and it's going to have some size L, and that's going to depend on T. Now, the only things that the shock wave care about are the initial energy of the shock, the mass density of the air that it's moving into, and time. It does not care about the pressure. Why not? Because pressure is carried by sound waves. And this is moving way faster than the speed of sound. So a sound wave can't come back up and perturb anything that's going on in here. If I have some large pressure here, the stuff inside the shock doesn't know about it. It can't, because the material is getting carried away faster than the sound speed. So there's no way for that sound wave to swim back upstream. So only the mass density matters. So the temperature of the medium doesn't matter, the pressure doesn't matter, only the mass density matters. So we want to find a function of length that depends only on energy, density, and time. And we'll do this using dimensional analysis. So I have 3 minutes. I can do this in 3 minutes. So the way this works is I say, okay, I want something that's a length. Units of length are centimeters. You can use meters if you like, but we'll keep it to CGS because that's what I do. This is going to be energy to the A, density to the B, time to the C. Have you guys seen this before anywhere? Anything like this?
Yeah.
Was that?
You showed us this before in extragalactic.
Yeah. What is energy? What's the units of energy in its base level? So get everything into the actual CGS or MKS, whichever you like. Get everything into the actual CGS units. So energy is not a fundamental unit.
Grams, centimeters squared per second squared.
And then density is grams centimeter cubed, and time is just seconds. And this is to the A, this is to the B, and this is to the C. So this is an algebra equation. This is actually 3 algebra equations now, because all my exponents have to make sense. So on the left-hand side, I have centimeters to the 1. On the right-hand side, I have centimeters to the, oh, this is a mess. Let's clean this up a bit. Let's do it again. From the E, I get grams to the A, centimeters to the 2A, seconds to the minus 2A. Let's do that a little bit more cleanly. We have grams to the A, centimeters to the 2A, seconds to the minus 2A, times grams to the B, centimeters to the minus 3B, and then seconds to the C. And this all has to equal centimeters. And each one of the units is an independent quantity, so they're all independent sentences. So look at the G. I've got A plus B has got to equal 0. That make sense? I got no gram on the right-hand side, and I've got some grams on the left-hand side, so they got to cancel out. Let's look at centimeters. Centimeters to the 2A plus, oops, minus 3B equals 0. No. 1, thanks. And then C equals, C, we got minus 2A plus C equals 0. Algebra, and you're done. What you are left with is the size is like energy, time, squared, times density to the 1/5. Don't write that down because I might have something wrong there. So you go through this algebra and you sort out what A, B, and C are, and then you get an equation that tells you how the size depends on time, and you didn't have to solve squat. All you did was look at the units. And this gets you most of the way there. This is why I give you a lot of like hand wavy problems where I make you like figure out how fast you blow and stuff, because the units are the important bit, and the numbers will work out as long as the units are, as long as you don't screw the units up too bad. Now here's where the New York Times messed up, because they had at the Trinity site, they published this beautiful series of photographs of this spherical explosion from the Trinity test, which was the first nuclear explosion. So they have this series of expanding shells, and this, and they put the time on each frame. Now, if you know the set-off-Taylor blast wave, oh, this is called the set-off-Taylor blast wave. If you're one of these guys and you already understand it, then the energy of the explosion is encoded in the position in this diagram, and how the front moves at the time, because it only depends on the energy and the density of air. And you know what density of air is? It's the same everywhere, but the energy is not. So, okay, I think that's everything I'm going to do today, and we'll do supersonic ping pong guns on Thursday. What was the other thing I said I was going to do Thursday? I said I was going to do group velocity. Yeah. Was there something else I was going to do Thursday?
Oh, you said that you were talking about the third jump condition or something like that?
Oh yeah, I'm just going to make you do that one from homework.
Okay, great.
It's more fun that way. For some value of fun.